6.3a, we're going to determine whether the conditions for a binomial random variable are met. So what binomial is refer back to the very beginning of the chapter, and we did the example about if you had 3 glasses in front of you, 2 had tap water and 1 had bottled water, what's the probability you could actually pick the bottled water? That was a binomial setting, and here's why. It arises when we perform several independent trials, so that was every student drinking and testing their water, of the same chance process. In our water example, it was a 1/3 chance. We record the number of times that a particular outcome occurs. We recorded it. And the 4 conditions for the binomial setting are this. You must state these. You're going to check what's called bins. This is a really good way to remember checking the conditions. The first is it binary? In all binary means, the possible outcomes for each trial can be classified as success or failure. So back to our water example. You either chose the tap water or you chose the bottled water. You either succeeded or you failed. Independent is the I. Trials must be independent of each other. Student 1, student 2, student 3 testing the water. We're fine. The N is the number. The number of N trials of the chance process must be fixed. Ours was fixed at a class of 21 students, so we had 21 defined. And the S is success. On each trial, the probability of success must be the same. Well, when student 1 drank the water and student 2 drank the water, each student had a 1/3 chance of picking the bottled water. So it met the binary condition, which means we can do a binomial probability on it. So if a variable meets those conditions, what does it mean to be an actual binomial random variable? Well, it's this. Binomial deals with the count of successes in a binomial setting. And this is actually important. Remember count, that refers to discrete or continuous. It's discrete. So binomial is considered a discrete type of thing because we're counting with whole numbers. So we have from trial 0 to n. In our water case, from 1 to 21 trials. Okay, what is the binomial distribution? Well, in terms of that, it's a probability distribution with the parameters of n and p. So you need to know what n and p are. We're going to use our calculator for this, but it's going to ask us for n and p. So jot this down. What n is the number of trials of a chance process. Okay, easy enough. In our water case, we had 21 trials. What is P? P is the probability of success in one trial. For our water case, it was 1/3. So we would type 21 and 1/3 in binomial, and it's going to give us some answers. Okay, let's do some practice here on is an event considered binomial or not. And again, remember bins. It's really important. So here's the scenario. We determine whether the random variable below or binomial. Justify your answer. Event A. We roll a die, a fair die, 10 times, and we're going to have X be defined as the number of 6s that show up. Okay, so is it binary? And what that means is there a chance of success? Sure, it's a 6 on one die. Well, what's failure? The failure is not a 6. So it's binary in that there's 2 possible outcomes. We either succeeded with a 6 or we fail with not getting a 6. Only two possible outcomes, so we're good on that. Okay, how about independent? We're doing 10 times. Is roll 1 independent of roll 2 and roll 3? Yeah, it just makes logical sense. Yes, past rolls won't impact future rolls. Now remember, back in chapter 5, we had to prove independence mathematically. We're going to start getting away from that, and it's going to be like, well, yeah, it's just obvious that they're independent, but we have to state that. N is the number of trials. Is there a fixed number of trials? Absolutely. There's 10 trials. It's fixed. It's set. And S is probability of success. Is there a fixed level of success that's the same for every single trial? Yeah, the probability of getting a 6 is fixed at 1/6 for every success. So this is considered a binomial distribution. And that's beneficial because if we know that, we would use that probability method to solve it. Next example. We shoot a basket 20 times from various distances on the court. Let Y be the event, the number of shots that we made. Okay, is this considered to be binary? Is there a direct success and failure? Sure, we're either going to make it or we're going to miss. So binary is met. You make the shot or you miss the shot. There's either one or the other going to happen. Are the shots independent? Well, we could assume that. We're going to actually say yes, one shot doesn't change the probability of the next shot, assuming we don't get tired or something of that nature. And number of trials. Is there a fixed number of trials? Yeah, there's 20. S, probability of success. Is it a constant probability of success? You have to be careful. We are actually at varying distances from the court. So a shot up front might be easier than a shot in the back. Therefore, the probabilities are going to be different. So no, this is not considered a binomial distribution because it fails the fourth requirement. More, we observe the next 100 cars that go by, and we're going to call the event C is the color. Okay, I'm just sitting on the side of the road and I'm looking at the next 100 cars and looking at their color. So is it considered binary? Is the color one or two, a success versus a failure? Well, if I'm just looking at the color, I don't know what color we're talking about. So there's going to be more than two possible outcomes for the color. Do you mean red, green, blue, white, silver? So on here, it actually fails the binary because there's more than two possible colors. Also, this problem has a second issue with it, in that if I'm looking at color, can I count the color? Do I record the color as a word or as a number? Well, I record the color as a number. This is not even a numerical type of outcome. So C is not a random variable since the outcomes aren't even numeric. The outcomes are actually words for this. So we would say, no, it's clearly not binomial. Let's do one last setup here and check your understanding. Let's look at these three. Are they considered binomial? And if not, where do they fail? Scenario 1, we shuffle a deck of cards. We turn over the top card, put the card back in the deck and shuffle again. Repeat this process 10 times. The event I'm looking at is the number of aces you observe. So in terms of binary, is there a success and a failure? My success, I get an ace. My failure, I don't get an ace. Perfect. Independent. I put all the cards back and start over every time. Yes, they're independent. N, fixed trials. Yep, there's 10. S, probability of success. Yes, the probability will always be the same of 4 out of 52. So this here is a Binns works, therefore it is a binomial distribution. Number 2, choose 3 students at random from your class. The event is Y, and it stands for the number who are over 6 feet tall. Okay, is it binary? Is there a success and failure? My success is you're over 6 feet tall. My failure is you're under 6 feet tall. So yes, it's binary. Is it independent? Well, you have to be careful here. Is it independent? Well, if you choose 3 students at random, when you choose that first student from your class, they're no longer there to pick from, so your sample size just got smaller. So in this case, the independence is actually broken because we're not replacing the student. So no, it is not independent. We are selecting without replacement is the huge issue here. And it's from a small number. So we have an independence issue. Number 3, you flip a coin. If it's heads, you roll a 6-sided die. If it's tails, you roll an 8-sided die. Repeat the process 5 times. The event W is the number of 5s that you roll. All right, let's look at this. Is it considered binary? You could say yes in this case. Success is you roll a head. Failure is you get a tail. Fine. Are they independent from each other? Sure, we start fresh every time. Is there a fixed number in terms of n? Yes, 5 times. How about the probability of success? Is that going to be fine? This is where the issue is. The probability of success is going to vary depending on if I get heads or tails. The probability of a 6-sided die versus an 8-sided die and my outcome is different. So this one fails under the probability of success and therefore is not a binomial distribution.